Record. Okay, now recording. And let me try to share the screen. Okay, so game plan for today is the next section, which is 15.2. I hope to complete 15.2, but if not, after a certain point, I will just stop and then I'll go to review session. Okay, now if I don't finish 15.2 and the questions stop, I might just go ahead and finish 15.2. Put it this way, my goal is to finish 15.2 by today. Okay, but again, I'll let you have some time for questions and answers. Get a little mini calendar. So here we are, Tuesday, 3/16, 15.2. Okay, and again, for Thursday, I'll let you have the entire class period, the whole class period for the exam. So once we join at 6:10, so a little bit before that, 6:04, 6:05, I will send the exam via Canvas announcements. And then you can join the class and just go ahead and get started. Okay, and you know the rules already for the exam. So have your camera on with a true background, no fake backgrounds. Camera needs to be on, mute yourself. If you have any question, put it in the chat. If you need to step away for bathroom, drink of water, whatever, just let me know. So if I see you, hey, where did so-and-so go? Are they cheating or whatever, right? So just let me know. You have the entire class period. And so as usual, I will close the class at our normal stopping time, which is 8:25, right? At which point you have 5 minutes, 8:30 to take a picture on your cell phone, click, 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 and send it to me, email it to me. And then you have another half an hour to submit the homework. So homework has to be in by 9 p.m. on Thursday, but I'll take it anytime after this class. And my general rule is you can submit it anytime after the period before. So after today, once class is over, I'll accept it anytime between end of class and what, Thursday at 9 p.m. I guess it was, we said. Okay. All right, so this is different. No questions next time. So I want you to be able to have the entire class period because some problems are just too long. Okay, so if there's any questions, it has to be tonight as soon as I'm done with my lecture for 15.2. Okay, so I'll let you have the whole class period. And again, I'm leaning toward that for exam 4 and exam 5. And well, we have to do that for the final exam, obviously, anyway. But I want you to be able to have that extra time. Are we ahead? I think we're a little bit ahead, but not as far ahead as you might think. It looks like I've been able to keep ahead from here, but don't forget, we lost that day here. So I'm trying to push back for the last regular exam to be Thursday, May the 13th, but we'll see how it goes. Okay, you can have their one cheat sheet, of course, one formula sheet, 8.5 by 11, double-sided, and a calculator. But after that, no more books, no notes, no people, no computers, no other aids that you can have. Okay, so any general questions about the exam? Okay. Again, I tend to give about 10 questions. So let's see. We're going to have what, 8 sections? So most likely one question per section, and then if I give 10 questions, then maybe there's another 9th and 10th one from somewhere. Okay. Again, the problems are very much similar, or maybe the exact same questions as the actual homework. Okay, you should not look at any question and say that was a surprise or I didn't see anything like that. That should not be the case. And I think most of you would agree with that for the previous exams that I've given. Okay. Yeah, the homework requirement, you must submit at least 70% of the homework, which really is not that hard because I end up doing a great percentage of it anyway, right? Sometimes I end up doing what, half the homework, more than half, or a little bit less than half. 70% is not that difficult to do. Okay, so any quick questions about that before I get started? All right, so on to more 15.2, and obviously whatever I covered from 15.1 last time and 15.2 today will not be on the exam. Okay, it'll be on the next exam, and that would be after the spring break. All right, so last time we did double integrals over rectangular regions, right? So if you look at the integrals that we did, right? So just casually looking, page 999, 15, integral from 1 to 4, 0 to 2, dy dx. Okay, they were constants. Okay, 17, integral from 0 to 1, 1 to 2, dx dy, 0 to pi over 6, 0 to pi over 2. It's basically a rectangular region that you're integrating over. Okay, so x goes from something to something, y goes from something to something, and they're constants. So for instance, x goes from 3 to 10, y goes from -5 to 12 or something like that. It's a rectangular region that we're integrating over. Now, however, we're going to integrate over general regions. Most general shape is something weird like figure 1. Okay. But if you look at what we're up against in the homework, so let me just quickly show you the homework. You can see they're not just constants for the x and the y. See, look at number 1, 1 to 5, 0 to x. Number 3, 0 to 1, 0 to y. Number 5, 0 to 1, 0 to s squared or whatever. Okay. So we're integrate over a region like that, or like that, or like that. Okay, page 1002. All right, a little bit of notation. Number 3, something called a type 1 region. What is type 1? Y goes between two functions of x, and then x is between two constants, a and b. Okay, that'll be something like this. Y is g1 of x, g2 of x. There's an upper function and a lower function. You did upper and lower functions in Calc 2, no doubt, when you integrate it, right? So this would be like y integrating from g1 of x to g2 of x, and then x goes from a to b. They call that type 1. Our quote unquote favorite, we like y as a function of x. Okay. What they call type 2 is the other way around. Type 2, see where it says dx dy? X is going from two functions of y. Okay, I can't point it out to you, but you see the inside says h1 of y, h2 of y, and then y goes from c to d. That would be a picture like so. Okay, so you have an upper function and a lower function. In this case, upper means further to the right. You had that concept in Calc 2, no doubt. Okay. And then y goes from a constant to a constant, c to d. Okay. And here's another such example. Upper function, lower function. Upper means further to the right. You know, if you would turn the picture 90 degrees, and I can't really do that here because it would hit my document camera. But if I turn it 90 degrees as much as I can, you see this is the upper and this is the lower, right? So if x is a function of y, and you should have seen some of that in Calc 2, right? The so-called upper function is the one that's further to the right and further to the left. Then y goes from c to d. Okay, so you can go either way. Sometimes you can go both ways. So then which is our preference? Well, we always like y as a function of x. So generally, if you have a choice between the two, I would pick type 1, where y goes from one function of x to another function of x, and then x goes from something to something, because we're used to it. We're less comfortable with x as a function of y, number 5. So x equals h1 of y to h2 of y, and then y goes from c to d. Okay. So as you can see, the way the rules of the game work, okay, the inside integral is allowed to be a function of the other variable. So see where it says dy? This can be a function of x. This can be a function of x. They're allowed to be constants, as we know from the previous section. But then the outermost function has to just be constants. So let's say if you see dy, this can be, say, 3x and x squared, but these have to be constants. The other way around, okay, number 5, dx dy, this can be a function of y, this can be a function of y, or they can be constants. Like this can be 3 plus y, this can be sine of y, but then these have to be constants. Okay, so the outermost integrals, which when you're writing it in the double integral, has to be the stuff to the left. the thing that's further to the left can only be constants for the double integral. These can be a function of the other variable. Likewise over here. Okay, so if you take a look at what we got in the homework. Okay, so before we actually do any problems, I'll just casually look through what we got over here. So notice the outermost integral are just constants. So look at number 1, 1 to 5. Number 3, 0 to 1. Number 5, 0 to 1. So the outside one, the one further to the left, are only constants, but the inside one can be a function of the other variable. So see for number 1, sorry, I can't point it because I'm holding up the book, but it says 0 to x, dy dx. Okay, so these two can be functions of x. If you have dx dy, these can be functions of y. So notice for number 3, inside is 0 to y. That's allowed. Or 5, they have dt ds. So for the inside one, dt, you can have a function of s. And it looks like they do, right? 0 to s squared. But the outside integral is just constant always, 0 to 1. In other words, this outside one, you're not allowed to have, x to 4x or something like that. The outside has to be just constants. All right? Then after that, they don't tell you how to set it up, but you have to know how to set it up based on the information that they give you. All right? So that's basically what's going on. Giving you a heads up further down the line when we do triple integrals. When you have triple integrals, the inside integral can be a function of 2 variables. Then you work your way out. Then the next one can be a function of only 1 variable. And then the outermost can only have constants, just as you might expect. Okay. Then our favorite, quote unquote, would be dz, dy, dx. So since we've been doing z as a function of y and x, we like that first. So our favorite, quote unquote, would be dz, dy, dx, because we've been doing z as a function of y and x. So let's pretend we had a triple integral. If there's dz, then the 2 limits can have functions of x and y for both of them, or they can be constants. Then let's say the next one is dy. Then the next one can have a function of x, but the outermost always has to just be constants. Okay. All right, so let's get our feet wet and start trying some of these problems here. Okay. So number 1, again, by order of operations, you go inside out. So when you see this double integral, you ignore the outside, you ignore the 1 to 5, you ignore the dx, pretend all you see is that. Integral from 0 to x, 8x minus 2y dy. Okay, again, let's think about the rules of the game, what's allowed. There's a dy here. That means these limits are allowed to have x, or they can be constants. Of course, you know they can be constants because that's all we did in section 1, right? Section 1, all 4 of these were numbers, weren't they? This was like 3, 10, -5, 12, or something like that, right? Okay, now when you have something like this, you don't have a rectangular region that you're integrating over. Okay, if the inside is dy, this can be a function of x, this can be a function of x, but the outside has to be constants. Okay, so only do this first. So you integrate with respect to y, which means x is a constant. So 8xy minus y squared, y equals 0 to x. Again, I like to put down y equals 0 to x so I don't forget which one I'm plugging in for. I'm not plugging in for x, I'm plugging in for y. Okay, is it true when you plug in 0, you get 0 for y? Yes. Okay, save yourself that step. Whenever you see that shortcut, go right to it. So I just plug in x. So that's going to be 8x squared minus x squared. So it's integral from 1 to 5, 7x squared. And of course, once you get to here, it's pretty much straightforward, right? This is home free. This is easy. That's even Calc 1 stuff. Right, so once you get the double integral to a single integral, then you should be saying, breathe a sigh of relief. I know what to do. Okay, knowing me though, I might mess it up. But anyway, let's see. So 7x cubed over 3 from 1 to 5. Factor up to 7/3. 5 cubed is 125 minus 1 cubed. So 7/3 times 124. Final answer is 868 over 3. Okay, what is that 868 over 3? It's the net volume of this thing. So it's between y equals 0 and y equals x, and then x going from 1 to 5. Okay, you don't have to write this down, but basically y equals 0 is the x-axis, y equals x, looks like that, and you're going from 1 to 5. So you're integrating over this region. I guess it's a trapezoidal region, right? Y goes from 0 to x, x goes from 1 to 5. So you're finding the volume, the net volume, I should say, above this region for this function. The net volume is 868 over 3. Why do I say the net volume? Maybe this is part of the time negative. Okay, I can't really tell offhand whether it is right now, but we don't really care. But the answer for the double integral is this. Okay, so there we go. Okay, number 5. Integral from 0 to 1, 0 to s squared, that's s squared, sorry, cosine s cubed dt ds. All right, so they don't have x and y, but dt ds. So the first thing I do is dt. That means these are allowed to have s's in it, and you can see they do, 0 to s squared. They can both be constants, which was the idea behind section 1, but the outside must be constants, 0 to 1. All right, so integrate with respect to t. This thing doesn't have any t, so it's constant. So it's t cosine s cubed as t goes from 0 to s squared. Okay, plug in 0, you get 0. Plug in s squared, you have s squared cosine of s cubed. Okay, now we can do substitution, okay? But if you do every single substitution, it would take a really, really long time for some of these, okay? I'm trying to show you if you can just go straight to the substitution without substituting, so to speak, okay? Think of the chain rule, okay? What's the derivative of s cubed? 3s squared. There's an s squared, that means you know you put a 3 here and a 1/3 outside, okay? But rather than actually doing the use substitution, which will take too long, okay, you know it's basically just going to be now the 1/3 sine of s cubed. Okay, so I'm going to try to show you that technique. So if it's a quote unquote simple substitution, hopefully you can say to yourself, oh yeah, if I take the derivative of s cubed, there's a 3s squared, that means I need a 3 here, 1/3 outside. Rather than doing the actual use substitution, just go right to 1/3 sine s cubed from 0 to 1. Okay, you still have the option of double checking by differentiating, right? What's the derivative of this? It's 1/3 cosine of s cubed times 3s squared. 3 knocks out the 1/3, and there's the s squared. Okay, so perfect. Again, plug in 0, you get 0, sine of 0 is 0. Plug in 1, 1/3 sine of 1. Okay, and just leave it. This is a sine of 1 radian, which is not a nice number, so we'll just leave it like that. Okay, so they pretty much gave you how to integrate here for questions 1, 3, and 5. Okay, there's some problems starting with 7 where they don't tell you how to integrate. You have to figure it out for yourself. Okay, so see how 1, 3, and 5, it's tailor-made, it's everything already there. So what if they give it to you like 7 or 9? Okay, you should be able to tell right away which way to go. Okay, based on the information they give you. So let's look at 7. Yeah, I was going to do 7. Look at this data. Based on that, what has to be the outside and what has to be the inside, right? The outside is x, the inside is y. See, how do I know that? Because these are constants. This is a function of x. So the inside has to be dy. Now, if both of these were only constants, then it doesn't matter by Fubini's theorem, right? So let's say this was 0 less than or equal to x less than or equal to 4, 0 less than or equal to y less than or equal to 7 or something like that. Then it doesn't matter. You can go either way. But the way it is right here, you have to have x on the outside. Is that right? Okay. I wasn't going to do 9, but I'll just talk about it For number 9, which one has to be on the outside? Y or X? Why? Because these are constants. X, however, goes from 0 to a function. So this has to be inside, this has to be outside. So this one has to be dx dy. This one, the outside has to be X, this one has to be Y first. So this one's going to be dy dx. Okay, that tells you which way to go. It has to be that way, right? Whoops. Sorry. Getting myself a little tangled up here with all my wires. All right, so double integral over the region D of y over x squared plus 1 dA. Okay, so this tells me outside x is going from 0 to 4, y is going from 0 to root x. Okay, for emphasis, I put the x equals, y equals. Technically, you don't have to put these x equals, but it's for teaching purposes, for emphasis. Okay, dy dx. Okay, and again, from now on, for most of this time, when I say dy dx, it isn't the calc 1 dy over dx, meaning derivative. Now when I say dy dx, it means this, dy times dx. Okay. All right, so if I integrate dy, that means x squared plus 1, or more accurately, 1 over x squared plus 1 is considered constant. So it's 1 over x squared plus 1, y squared over 2. Leave the 0 to 4 alone. Leave the dx alone. In other words, you do the inside out. Ignore the x and the dx. Just only look at that. Okay, so I have this. Y equals 0 to root x. Is it true when you plug in 0, you get 0? Yes. By the way, throughout this book, Mr. Stewart, the author, does a pretty good job of, making it quote unquote nicer for you students. Okay, a lot of these problems would get really overbearing if you didn't plug in 0. Like even just plugging in 1 here would make a much longer problem, right? Because you got all these extra things going on. But he does a pretty good job of not overburdening you with, extra stuff. He does a lot of, whenever there's a 0 that you can plug in, eliminate it. Okay, it saves a lot of work for double integrals. And later when we get to triple integrals, you'll really appreciate that when you got to do a triple integral, right? All right, so just plug in radical x. So I've got radical x squared. Well, what's radical x squared? Just x. Okay, so I'll take the half out. It's going to be x over x squared plus 1. Okay, so again, think of the u substitution. Okay, if you did u equals x squared plus 1, du equals 2x dx, right? So put the 2 here, another half outside. Okay, but rather than actually doing the u substitution, that was a u. So I'm going straight to ln absolute value of x squared plus 1. Okay, so again, you're doing this thing. That would have been the u. Okay, so if you think of how it's going to work, again, u substitution, u equals x squared plus 1, du is 2x dx. I need a 2 here, half outside, so now there's a 1/4 in front. It would be du over u, which is your natural log. Okay, but rather than doing all that, because it take too much extra time, believe me, it saves a lot of time if you can do this quickly. So it's ln absolute value of x squared plus 1. And again, if you don't believe me, you can just differentiate this and see if you get it, right? What's the derivative of this? You go 1/4, 1 over x squared plus 1 times 2x. That 2 is going to cancel that 4, leaving me with 1/2, and there's the x. So it works. Okay, plug in 0, you're doing ln of 1, which is 0. So just plug in 4, 1/4, natural log of 17. And there we go. All right, now for a much more difficult problem, or set of problems, starting with 19. Okay, so I'm done with 1 to 9. And what about these problems? So what are we up against now? So 19, y squared dA. D is a triangular region with vertices 0, 1, 1, 2, and 4, 1. So that's what I'm integrating over. double integral of y squared dA. Okay, so here's what I did. 0, 1, 1, 2, 4, 1. This is the region. So I'm integrating over this region. There's a function above it. And let me double check. The function is y squared. That's always going to be positive, right? So yes, we are finding the volume underneath the function, whatever it looks like, just within this triangular region. Okay, so again, notice the whole new world of possibilities opens up. Okay, and now once you integrate on this, again, think back to Calc 1 and Calc 2, we're only integrating over an interval, right? You only integrate from A to B. Is that all, right? You only integrate from 23 to 7 to 45, or you're integrating from negative pi over 2 to 3 pi over 2. Okay, now we can integrate over square regions, triangular regions, circular regions, right? When you get to 3D, you're integrating over spheres and boxes and cubes and ellipsoids and all kinds of different things, right? So a whole new world of possibilities opens up, which now it seems like what you did in Calc 1 and 2, you only integrate over just an interval. It's almost like saying, is that all? You're only integrating from 3 to 10. Now we're integrating over triangular regions or whatever. Okay, so there's some function above it, whatever it looks like, we're trying to find the volume. Okay, so I had to come up with equations of these. Okay, so this one is easy. This is just y equals 1, going from 1 to 4. How about this one? Okay, so this y-intercept is 1. Slope is 1, you can see. So that's y equals x plus 1. This one is the hardest of all, and it doesn't really come out nice. So from algebra 1, how do I find the equation of the line joining 2 points, right? So 1, 2, and 4, 1. So first I find the slope is negative 1/3, y2 minus y1 divided by x2 minus x1, negative 1/3, right? And then I did the point slope form, y minus y1, y minus 2 equals m, negative 1/3, x minus 1, little bit of cleanup, y equals negative 1/3 x plus 7/3. Okay, so that's what I have over here. Okay, and a quick double check. If this is correct, which I could doubt myself if the answers come out so bad, well, this point and this point should satisfy that line. So 1, 2. If I plug in 1, I get negative 1 plus 7 is 6. 6 over 3 is 2. That works. And if I plug in 4, I should get 1. Plug in 4. Negative 4/3 plus 7/3 is 3/3. That is equal to 1 also. Okay, so here's the region in question. Now, why am I drawing the arrow like this? I'm going to do this as type 2. Because if I do type 1, okay, which would be going this way, it would be upper minus lower. I'd have to split it into 2 pieces, wouldn't I? From here to here, the upper function is x plus 1. This is the lower function. But then from here to here, the upper function becomes this one. And the lower function is still this one. Okay. So I'm going to treat it as type 2 going this way. That way, the upper function is this one. I'm going to write this as x is a function of y. That shouldn't be that hard. I'm going to write this as x is a function of y. That's easy. I can do that right now. How do you isolate the x? X is y minus 1. Do the same thing here. And I can do the entire problem without splitting it into 2 regions. So that would be one reason why I would split this into so-called type 2. X is a function of y. Yes, we're less comfortable with that. But at least we only have to do one integral instead of splitting it. If I were going type 1, our favorite, so to speak, y is a function of x. Well, from 0 to 1, this is the upper function. Then from 1 to 4, this is the upper function. Okay, so we have to do a little bit of extra algebra. Y equals x plus 1, subtract 1, x equals y minus 1. Okay, and then this one, see, I multiply both sides by 3. 3y equals negative x plus 7. Add x and subtract 3. X equals negative 3y plus 7. Okay, so this function is x equals negative 3y plus 7. I'll write that down now. X equals negative 3y plus 7. That's another way of saying this line, but it's x as a function of y. And we know this one as x equals y minus 1. So upper function, lower function as type 2, so to speak, lower, upper. So if I'm going this way, x has to be first. So it's dx dy. So the double integral x goes from y minus 1 to negative 3y plus 7. Lower function is y minus 1. Upper function is negative 3y plus 7. If it's hard to see that, look at it this way. Then you say, oh yeah, that's the upper, that's the lower. And I'm not going to integrate from 0 to 4. That would be for x. But the outside integral is with respect to y. So y goes from 1 to 2. So here's the way I have to set this one up. Y squared dx dy. X equals y minus 1 to negative 3y plus 7. And y goes from 1 to 2. Okay, now I'm going to try to show you this as a quote unquote shortcut. This is considered a constant as far as x is concerned, right? So if I only look at this, what's the integral of y squared dx? It's y squared x. You would factor out the y squared. You would plug in this. You subtract that. Basically, it's the length of the interval. Okay, in fact, I'll do a quick timeout and remember something like this from Calc 1. Okay, so integral of k dx from a to b is kx from a to b, which is kb minus a, or the length of the interval. I'll raise that up for you here. Right? So if you integrate a constant, you can put kx, a to b, k times b minus a. It's k times the length of the interval. It's more suggestive if I go like this. F of x is, whoops, f of x is k from a to b. Right? You say, oh yeah, it's just the area of that rectangle, which is k times b minus a. So another shortcut, if you integrate with a constant, it's that constant times the length of the interval. Length of the interval means upper minus lower, b minus a. We will use that shortcut. Believe me, you really want to use such shortcuts when you get to more complicated double integrals and triple integrals. Right? So again, if you formally go by the rules of the game, so to speak, integral of k would be kx. Then you plug in b, you can factor out the k, it'd be k times b minus a. So that's what's happening over here. When I integrate y squared, that's constant as far as x is concerned. So the integral is y squared times upper minus lower. The so-called length of the interval is negative 3y plus 7 minus parentheses y minus 1. Okay, that's 7 minus a minus 1 is 8. Negative 3y minus y is negative 4y. Distribute the y squared. So 8y squared minus 4y cubed dy. The rest is pretty straightforward, right? Integral from 1 to 2. So that's going to be 8y cubed over 3 minus y to the 4th. 8y cubed over 3 minus 1 to the 4th from 1 to 2. This time we don't get to plug in 0 and 1, but at least it's a last integral. Okay, so Mr. Stewart was kind enough to make it, okay, if I don't get to plug in 0, at least it's the outermost integral, which is the quote unquote normal integral. Okay, plug in 2. 8 times 8 is 64. 64 over 3 minus 2 to the 4th is 16. Minus plug in 1, 8 thirds minus 1. So 64 thirds minus 8 thirds is 56 over 3. Negative 16 minus a minus 1 is minus 15. That's 45 over 3. Final answer is 11 over 3. Right, the problem's finished, but you see what we're getting at here, very powerful. What is that x over 3? It's the volume, okay? Only over this region. So you have this triangular plot of land. Your house looks like this, the plot. There's a function above it. The function is y squared. We know it's positive, y squared, right? So there's some volume underneath it. What is that volume? 11 over 3. Okay. All right, 21 is kind of a weird problem, but we're going to take advantage of symmetry, so to speak. Okay, double integral of 2x minus y dA. D is bounded by the circle with center at the origin and radius of 2. By the way, this would be a situation where you want to switch over to polar coordinates. We'll be doing polar coordinates in the next section. Okay, but I'm going to reason this out with a little bit of symmetry here. So this is what it looks like. This is what I'm integrating over. There's a circle. 2x minus y. I'm allowed to split it into 2, right? Double integral of 2x dA minus double integral of y dA. 2x. This is a perfectly symmetric shape. This is symmetric also. 2x. Whatever this graph looks like, there's exactly as much above as below the xy plane, or the plane of the floor, so to speak. Okay, see if I can convince you of that. Let me go this way. Okay. We have symmetry with respect to the y-axis, correct? The function 2x. So if I have a point over here, which is 1, this would be -1, right? 0.1, there's a corresponding -0.1. That's going to be true all throughout the circle, correct? So there's just as much graph above as below, even over here. Okay. The height would be 1, this would be -1. They would quote unquote cancel each other out. Somewhere here it would be 0.7, -0.7. You have exactly the same number of positives and negatives, so the net volume would be 0. And the exact same logic applies for the double integral of y. You have just as much graph above and below the xy plane in the y direction. Okay. Over here, the height is 2. Over here, it's -2. They would cancel each other out. Every point has a corresponding point that quote unquote cancels it out. Here, the height is 1. Here, it's -1. Here, the height might be 0.7. Here, the height might be -0.7. So whatever the graph looks like, there's exactly as much graph above as below. So the answer is automatically 0. It's almost like there's nothing to do once you realize that. The hard part is to realize that. To actually work this out would be quite a bear for now. It'll be easier when we switch to polar coordinates. But the answer is that because of symmetry, every point above the XY plane has a corresponding point below the XY plane. So when we take the net volume, then the volume is automatically 0. Okay, which basically means there's nothing to do. Okay, now that was only if you have that symmetry. Now, if this was 2x squared y or something like that, that would not be true. But just for this one problem, we can make that statement. Okay. Okay, 25. Yes, as you can see, I messed up the first time I did it, but what else is new? All right. Under the surface, z equals xy, and above the triangle. Okay, so there's that triangle stuff again, right? 1, 1, 4, 1, and 1, 2. So let's see what we got there. Okay, here's 1, 1, 4, 1, 1, 2. Triangular region. There's a graph above it. This time it's definitely positive. The function is x times y. Within this plot of land, x is positive and y is positive. So we're definitely talking about above, right? So we are talking about the volume in this particular case. Okay, so find the volume of the given solid that we have here. All right, so this is easy. That looks like y equals 1. This is x equals 1. And this one got to do a little bit of y2 minus y1 divided by x2 minus x1, right? So the points are 4, 1, and 1, 2. Slope is negative a third. 2 minus 1 divided by 1 minus 4. Or you can just go from here to here and say it's over 3 down 1. So the slope is negative 1/3. Okay, so y minus y1, I use the point 1, 2. Y minus 2 equals negative 1/3 x minus 1. Do a little bit of touch up. Y is negative 1/3 x plus 7/3. See, negative 1/3 x plus 1/3 plus 2. So 2 1/3, 7/3. Okay, double check if this is correct. 4, 1 should work. Plug in 4. Negative 4/3 plus 7/3 is 3/3 or 1. That's correct. And when I plug in 1, I should get 2. Plug in 1. Negative 1/3 plus 7/3 is 6/3. That is 2. Okay, so forget that. I botched it up. Okay. And as you probably know by now, if you set up an exam and you get most of it right, don't overly sweat. If you say, oh no, I remembered, I did some calculation wrong and I totally messed up. No, you did not totally mess up. If you have the setup correct and you show me all the proper work and you get a calculation error, I will give you most of the credit. You can botch this up just as well as I can botch this up. And I'm one of the best botcher-uppers, I guess, if that is such a word that's out there. So yeah, don't overly, stress if after an exam you say, oh, I just remembered I messed up a calculation here. I mess up all the time. Okay, so if you get the idea correct, you'll get most of the credit. So not to worry about that. Okay. All right. So since it's like this, I'll just go type 1, my favorite. So y goes from what? 1 to the function, which is this, and then x goes from 1 to 4. All right. So here we go. Y goes from 1 to 7/3 minus 1/3 x. That's probably a little bit easier to plug in. And then x goes from 1 to 4. That should be a 4 there. It might look like a y. 4 dy dx. Okay, yeah, let me go back. Now that I'm finished with this page, do a focus job for you quickly in case you can't see anything here. And I know I'm going fast, but you can always pause the video anytime that you want. So I only need to expose it just for a brief moment in case you can't see all that. And that. And you don't need to see the bottom of that because I messed up. Okay. All right, so back to here. So integral of x, y, dy, that means x is a constant. It's x, y squared over 2. Okay, leave the x equals 1 to 4 alone, leave the dx alone. Okay, so this one's not so nice. Take the half out. Half comes out. So I have 7/3 minus 1/3 x squared minus 1 dx. Okay, that's going to be very messy. So I did a little trick. Okay, I decided to multiply inside by 9 and outside by 1/9. Okay, if I square this out, right, 7/3 minus 1/3 x, the denominator is going to be 9. If I multiply by 9, I'm basically just squaring 7 minus x. Do you agree? That just makes it a little bit nicer. Okay, it's going to be 7/3 squared, 49 over 9, right? Minus 2 times 7 times x divided by 9 plus 1/9 x squared. They all got a 9. So I don't like the 9. So multiply by 9 here and 1/9 here. It just makes it nicer. So I'm going to get 49 minus 14x plus x squared, and then minus 9. 49 minus 9 is 40. Okay, then I'm pretty much home free. All right, so 1/18, 40x minus 7x squared plus x cubed over 3 from 1 to 4. 1/18, plug in 4. 160 minus 7 times 16 is 112 plus 64 over 3 minus parentheses, plug in 1. That's easy. 40 minus 7 plus 1/3. Okay, let's see. If you work it all out, 64 over 3 minus 1 over 3. That's 63 over 3, which is 21. Okay, combine all the rest of the stuff. Believe it or not, it comes out to be 2 if I did it the right way. Well, I checked the back of the book. It should come out to be 2 if I did all this other stuff here. 160 minus 112. That's 63 over 3, which is 21, minus 40, minus 40 minus 7, and all that stuff. So hopefully it comes out to be 2. Okay, that's the volume underneath the function z equals xy on this triangular region. There's some graph above it, right? That volume turns out to be 2. Okay. All right, it's a good time to break. Okay, so I don't think I'll go that much longer. I'll do some problems after the break, and then I'll leave it open for questions and answers. So think of any questions you might want to have in review for the exam on Thursday after the break. Okay, so we'll break at to our usual 7:10. How about 7:10-ish? Okay. Okay, folks, let's try to pick up where we were. So,
Excuse me, Professor.
yes, Rashad.
Can you show the end of problem 25 there?
End of
And
25.
yeah,
Okay,
yeah.
right here. Yeah, I think that's it. Let me double check. Yeah.
And you multiply that first um, integral by 9.
Back over here.
Yes,
Yes. So this thing, I didn't like to work with the fractions.
right.
And then all the denominators were 9. So I decided to multiply by 9 and 1/9, which is allowed. That just gives me nicer numbers.
Okay, okay, I got you. Okay, thanks.
All right. Welcome. All right. So let me do some more problems. I don't know how long that would take, maybe half an hour, 45 minutes, something like that. And then let's open it up to questions and answers. Because remember, there's no question and answers for Thursday. I'm just going to give you the whole time for the test. So any questions would have to be tonight. Okay. And let's see, double check the chat. Okay, I think I'm caught up. All right. So 31. Okay. Bounded by the cylinder x squared plus y squared equals 1 and the planes y equals z, x equals 0, z equals 0 in the first octant. Okay, so first octant means I'm integrating on the first quadrant. Y equals radical 1 minus x squared. Okay, the function was y equals z or z equals y, so we're integrating y, so to speak. Okay, so let's show you back again, problem number 31, I think it was. Okay, see where it says y equals z? That's the same as z equals y. Okay, so remember we have z as a function of x and y. That's equivalent to Calc 1 and Calc 2, where you're integrating y equals f of x. Okay, that's the area under the curve. So now we're finding the volume under a surface, z as a function of x and y. We're integrating the height, and the height is z in general. So that's why we're integrating y. Right? So it's nice. So z is a function of x and y, it's the height. So now we know why we're integrating, or why we set our x, y, z coordinate system so that z is this way, because we want z as a function of x and y. Think of the xy plane as the floor, and then the z values are the heights above it. Just like in Calc 1, when you were integrating f of x, you're integrating y, right? You're integrating the heights. So same thing, we're integrating the heights. Right, so this is what it looks like in the first quadrant. The volume underneath it will be in the first octant. You said, okay. All right, so integral of y is 1/2 y squared from 0 to radical 1 minus x squared dx. Plug in 0, you get 0. If I square a square root, I just take off the square root. So I'm integrating 1 minus x squared, and that's very easy. Take out the half. Okay. And I'm guessing all of you, once you look at that, you breathe a sigh of relief. So, okay, I can do that. That's easy, right? Of course, whenever I say that, watch me mess up. But anyway, so that's going to be x minus x cubed over 3, right? 1/2 x minus x cubed over 3 from 0 to 1. Plug in 0, you get 0. So just plug in 1. 1/2 of 1 minus 1/3. 1 minus 1/3 is 2/3. Half of 2/3, 1/3. Okay. What is that 1/3 geometrically? It's the volume underneath the function, whatever this function looks like. Z equals y. There's some graph above it. The volume underneath this, we're integrating over this quarter circular region, is 1/3. Okay. Again, please notice the wide variety of things that you're going to be integrating over. Not just in Calc 1 and Calc 2, you're just integrating over an interval from A to B. You can integrate over circular regions or quarter circle regions or triangles, rectangles, all kinds of stuff. Okay. All right, that's that. Now for 45, some rather unusual problems at the end. 45, sketch the region of integration and change the order of integration. Sometimes we want to change the order of integration. Doesn't matter what the function is. So if you look at 45, 47, 49, it just generically says f of x, y, right? Meaning we don't really care what the function is. We're just focusing on the region of integration. Okay, so I'm up to 45 to 55 at the end, so I'm pretty close to the end. All right, so dx dy means x goes from 0 to y goes from 0 to 1. So you work inside out. Ignore that for a moment, ignore that. So x goes from 0 to y. X equals 0 is the y-axis. X equals y or y equals x is like that. And then y goes from 0 to 1. So there's the region as so-called type 2. Now switch it around so that it's type 1, going this way. So y goes from something to something. So in that case, y goes from x to 1, and then x goes from 0 to 1. So that's how to do that one. Okay. Why would you ever want to do that? Sometimes you have to do it because the integral is easier one way versus the other way. Okay. Sometimes it's impossible to do it one way, but if you switch it, you might realize, oh, it's not so bad after all. Right? So these two are the same. So this one, you can write it as either type 2 or type 1. So type 1, x goes from 0 to y. Here's x equals 0. Here's x equals y. And then y goes from 0 to 1. So this is the triangular region. That's so-called type 2, from lower to upper. Now, if I go type 1, y goes from lower to upper. This is y equals x. This is y equals 1. And then x goes from 0 to 1. Okay. Here's 49. It said integral from 1 to 2, 0 to ln x, f of xy, dy, dx. Switch the order of integration. All right. So y equals 0. That's the x-axis. Y equals natural log of x. Now, if y equals natural log of x, that means x equals e to the y. Remember, you can exponentiate both sides, right? You have to solve for x. If I put an e here, right? Exponentiate, e to the ln x is x, so x is e to the y. Okay, so as type 1 like this, y goes from 0 to ln x goes from 1 to 2. Switch it to type 2. Okay, so I have to figure out what this point is. Here, x is 2. If I plug in 2, then I get natural log of 2. Right? So x is going from here to here. So the lower function is e to the y. The upper function is x equals 2. So the inner integral is x equals e to the y to 2. And then y goes from 0 to natural log of 2. And this would have to be dx dy. Okay, so this is how you would switch the order of integration. Obviously, we're more comfortable y is a function of x. We've been doing that since, many years ago. We've always done y equals f of x, y equals f of x, y equals f of x. So maybe our brains are a little bit messed up when we have x as a function of y, but this is the way it would work out. Okay, so first I drew the picture, y equals 0, y equals ln x. Okay, and then x goes from 1 to 2. Now, how do I take that region as type 2? Right, if I turn it 90 degrees, okay, this is the lower function, x equals e to the y. Upper function is x equals 2, and y goes from 0 to natural log of 2. Whoops, where'd it go? Lost my place here. Yeah, so here we go. I'll find it. Yeah, here we are. All right, then we'll actually need that for 51. Okay. 51, evaluate the integral by reversing the order of integration. And there's a good reason for that. Okay, so 51, integral from 0 to 1, 3y to 3 of e to the x squared dx dy. You might recall from your Calc 2, you can't easily integrate e to the x squared dx, or there's no closed form for that. Okay, you can't integrate e to the x squared unless you're willing to go through series. Remember at the end of Calc 2, you were able to write this as a series, right? Like e to the x was 1 plus x squared over 2 factorial plus x cubed over 3 factorial, all that stuff. Remember that? Then you would substitute x squared in its place. So you'd have an infinite series, but otherwise you couldn't do this. So as it stands, you can't do it, but you will be able to do it if you can switch the order of integration. Okay, so here we go. X is going from 3y to 3. X equals 3y means y equals 1/3 x, right? So I draw y equals 1/3 x. Here's x equals 3. So here is the region as type 2. Dx, x is going from the lower function, 3y, to the upper function, 3. And y is going from 0 to 1. How do I write it as type 1? Okay. And by the way, how did I get this? Well, x equals 3. If 3y equals 3, then y equals 1. Remember, this is x equals 3y, which will be y equals 1/3 x, right? So how do I find a y coordinate? We'll just plug in 3. 3 equals 3y, y equals 1. So as type 1, it'll be dy dx, and it'll work out because I'll get the extra x that I need. So if I go this way, the lower function y equals 0 up to y equals 1/3 x, and x goes from 0 to 3. Now it's doable because I'm integrating e to the x squared dy. This is a constant as far as y is concerned. So the integral is the length of the interval, as I mentioned before. So what's the length of this interval? 1/3 x. So I have to sneak in a 1/3 x up here. And now that there's an x there, it just becomes a simple u substitution. Okay, take out the 1/3. Okay, if I do u equals x squared, du is 2x dx, right? The 1/3's not there anymore. I need a 2, so 2 inside, 1/2 outside. So you know that was going to be e to the u, right? Just write it as e to the x squared. So outside I now have 1/6 e to the x squared from 0 to 3. Okay, and now it should be pretty straightforward. Okay, again, you can double check by differentiation. Right, what's the derivative of this guy? You would put 1/6 e to the x squared times 2x. 2 times 1/6 is 1/3, and there's the x. So it works. Okay, so 1/6, plug in 3, e to the 9th, plug in 0, e to the 0 is 1. So final answer is 1/6 of e to the 9th minus 1. All right, then 55, and that's the last one. Then I'm done. Okay, so I'll be done in another 5 minutes or so. So if you can think of questions you want to ask for review, then be ready to bring them up because I'll be done after this last problem, okay? So I'll be done with what I was trying to accomplish, which was to finish 15.2. Okay, so Thursday, all we have is a test. So I guess we'll do 15.3 and 15.4 perhaps by the time we get to spring break in a week after that. All right, so 55. You can see how bad it looks, right? 55, 0 to 1, arc sine y. We don't like that. Arc sine y, pi over 2, cosine x radical 1 plus cosine squared x dx dy. Okay, x equals arc sine y means y equals sine x, right? That means the same thing. And we're going up to x equals pi over 2. Here's x equals pi over 2. Here's x equals arc sine y, or y equals sine x. Plug in pi over 2. Sine of pi over 2 is 1. So this is the way as it's given, so-called type 2. The lower function is x equals arc sine y, which means y equals sine x. And you're going up to pi over 2. And then y, the outside one, y is going from 0 to 1. Much nicer to go type 1, y goes from 0 to sine x. I like sine x. And then x goes from 0 to pi over 2. And I messed up again, but what else is new? So x equals 0 to pi over 2, y equals 0 to sine x of cosine x, radical 1 plus cosine squared x, dy dx. Okay, much nicer. All right, I'm integrating with respect to y. This doesn't have any y, so this is treated like a constant. So when it's constant, cosine x radical 1 plus cosine squared x times the length of the interval, sine x minus nothing, sine x. Okay, so again, this is all constant as far as y is concerned. So just leave it alone. Cosine x radical 1 plus cosine squared x times the length of the interval, sine of x minus nothing, is sine x. Okay, again, if you're not happy with that, the logic is, okay, if you formally go through it, right? This is all constant. So the integral is blah, blah, blah times y. Then you would plug in sine x minus nothing. So there it is. Okay, this one's much more complicated. I'll actually do the substitution, but fortunately we're down to a single variable. So it's just like Calc 2 now. Okay, the derivative sine is, derivative cosine is negative sine. That has a cosine, that has a cosine. So substitute, let u equals cosine x. Du is negative sine x dx. Need a negative 1 inside and outside. Change the limit of integration. I'm going from 0 to pi over 2. If x is 0, u is cosine of 0, which is 1. If x is pi over 2, u is cosine of pi over 2, which is 0. So I'm integrating backwards, but you remember that happened a lot in Calc 2, right? There's a negative, and it goes from 1 to 0 of u radical 1 plus u squared du. And this happened a lot in Calc 2, didn't it? This is a negative and this is backwards. Just reverse it and make it a positive, right? So it's positive, and it go from 0 to 1, u radical 1 plus u squared du. Okay, you could do another substitution. I guess you can't call it a u substitution anymore because you've already used up u. Okay, I suppose you can call it a t substitution. But again, let's try to reason it out. Trying to get you to do the u substitution without doing the u substitution. Okay, what's the derivative of 1 plus u squared? 2u. There's the u. I need a 2, so put a 2 inside and a 1/2 outside. That's not a negative, sorry, that's part of an equal sign. 1/2. So I'm basically integrating, call it t to the 1/2. So that's t to the 3/2 divided by 3/2 means times 2/3. So it's 1/2, 2/3, 1 plus u squared to the 3/2 from 0 to 1. Okay, a quick double check if you're not convinced of that without actually doing the substitution. Okay, ignore the half is already there. What's the derivative of 2/3, 1 plus u squared to the 3/2? So if I differentiate this, 3/2 times 2/3 is 1. 1 plus u squared to the 1/2, which means square root, times 2u. So it works. Okay, and that 2 would knock out that 1/2 there. Okay, so 1/2 times 2/3 is 1/3. Plug in 1, I have 2 to the 3/2. Plug in 0, you have 1 to the 3/2, which is 1. Okay, the best way to write something to the 3/2 power, those of you who took me for Calc 2, know, write it as 2 radical 2. 2 to the 3/2. 2 is like 2 to the 1, right? And maybe I'll write it 2 to the 1. And square root is 2 to the half. So if we raise something to the 3/2 power, you can think of it as 2 to the 1, 2 to the half. There's 2 to the 1, 2 to the half. So final answer is 1/3, 2 radical 2 minus 1. And there we go. Okay, I'm finished, folks. So let me just go back and do the focusing thing. But otherwise, the rest of the time, you can ask me questions in preparation for the exam. Okay, so next time we'll just go straight to the exam, nothing else. Chapter 14, submit the homework either immediately after class or anytime between right after class and half an hour after Thursday's class, which would be what we said 9 o'clock. Since we end at 8:25, so you have until 8:30 to submit the test, and then 9 o'clock to submit the homework. Okay, so if you want to either unmute yourself or start typing stuff in the chat, you may, but let me just give you this focus thing here for your benefit. And there's that. And more. And more. And that. And then here. I know I'm going fast, but again, you can look at the video and pause anytime you want. Okay, that'll do it. All right, so I will now let you ask any questions in preparation for the test. So you can either put it in the chat or unmute yourself. And if there isn't anything, then we're done, folks. Okay, so again, next time, no questions. We'll go straight to the test. A little bit before class starts, 6:05-ish, I'll send the exam via Canvas announcements. And then we'll just go straight to the exam after that. Okay. All right, so see something started. Okay, I got a request for 14.329 and 14.355. Okay, so let me start with that, see what that's about. You can keep typing if you wish, but let me see what that's about for now. We're still recording, by the way. Ah, 14.329. Yeah, that required part of a fundamental theorem of calculus part 1. Sorry, I should have left that out. Okay, skip 29. I should have told you that ahead. So if you tried it and you got it, great. Okay, I should have realized that I shouldn't have given you that one. Okay, so skip 29. Oh, did it say skip 29 in the assignment? I'm not sure if it said it or not. Oh yeah, skip 29. It's easy to forget once you get in a row. So yeah, I didn't want that one. So all right, no worries. So 14.355. Find all the second partial derivatives. Okay, so 14.355. Let's see what that one's about. Z is equal to y over 2x plus 3y. Equals y times 2x plus 3y to the negative 1. Okay, so z sub x, partial with respect to x, y is constant, so negative y, 2x plus 3y to the negative 2 times the derivative of the inside with respect to x, which is 2. So clean it up, negative 2y over 2x plus 3y quantity squared. Okay, but I'm also going to write it like this, because that might be more helpful. Z sub y, oh boy. Looks like I'll just do the quotient rule. Bottom times derivative of the top with respect to y, which is 1, minus the top times derivative of the bottom with respect to y, which is 3, over 2x plus 3y squared. Now multiply by 1, that's gone. So it's 2x plus 3y minus 3y, right? So the 3y's cancel out. 2x over 2x plus 3y quantity squared. But again, let me write it like this because I might need it that way for the second derivatives. Okay, so now zxx, I take the derivative with respect to x and differentiate again with respect to x. That means negative 2y is a constant. Okay, so negative 2 times negative 2 is 4y, 2x plus 3y to the negative third, times the derivative of the inside with respect to x, which is 2. So that's going to give me 8y over 2x plus 3y cubed. Okay. zyy, I take the derivative with respect to y, here it is, differentiate again with respect to y. That means 2x is constant. Negative 2 times 2x is negative 4x. 2x plus 3y to the negative third times derivative of the inside with respect to y, that's 3. So that's going to be negative 4 times 3, negative 12x divided by 2x plus 3y cubed. And then the mixed partial, I can either do zxy or zyx. They're equally bad. Looks like I have to do the product rule. I could do the quotient rule from here, I guess. They're both not very nice. zxy, which is equal to zyx. Let me take the derivative of this since I can see it. I can't see this one anymore. So product rule. First function times derivative of the second, negative 2, 2x plus 3y to the negative third, times the derivative of the inside with respect to x, 2, plus second function, 2x plus 3y to the negative 2, times derivative of the first function with respect to x, 2. Okay, that's just some cleanup. Hopefully I didn't mess up. So let's see, 2 times negative 2. So if I do it right, I think it's negative 8x over 2x plus 3y cubed. And what is this thing? 2 over 2x plus 3y squared. Okay, so unless I messed up, that's what I got for the answer, it looks like. Okay. Okay, I don't see anything else right now. So any other questions, please? Otherwise, that's it. Any more questions? I'll wait a little longer, make sure I didn't miss anybody. Okay, I don't see or hear anything, so we're going to call it a night. All right, that'll be it, folks. So you may start turning your homework starting now, and next time we'll go straight to the exam. No new stuff. You'll have the entire class period for the exam. All right, have a good night, and we'll see you on Thursday for the test. Okay, good night, everybody.
Thank you.
Thank you.
Thank you.
Thank you,
Good night.
Professor.
Thank you. Good night.
Thank you. Good night.
Night.